let's do this one. So let's calculate the following. Double integral 0 to 9, and from, bless you, the square root of y to 3 of 1 over the square root of x cubed plus 9 dx dy.
If you watched the video I posted over the weekend, this was the last problem I left at the end of the video. It was like, you should try this one on your own if you have a chance. If you didn't watch the video, that's totally fine. I do recommend watching it. I talk a lot about double integrals. We can certainly backtrack on some of that info if you want me to, but let's start off with this problem and then we'll kind of talk about things. So here's double integral. And the way we read this is first we're going to integrate with respect to x. There's your inside. And then after we do that, we're going to integrate with respect to y. And just like differentiating with respect to x or y, you treat the other variables as constants. The same thing is true when you integrate with respect to x or y. The issue here is that I don't know how to integrate 1 over the square root of x cubed plus 9. And I don't think it's actually possible to integrate that with respect to x. So typically, if the integral you're trying to do is impossible in the order it's written in, it usually means it's probably a good idea to change the order of integration. And we're going to do that. We're going to change order of integration. To really be able to do that, we have to be able to draw the region in the xy plane that we are integrating over. I'm going to point out that these limits of integration, the inner limits, well, since that's a dx on the inside, that's saying x is going from the square root of y to 3. And my outer limits of integration are y equals 0 to y equals 9. So really, if we have to change the order of integration, we always start off by just drawing the region that we are integrating over. So let's see, I've got x equal to the square root of y, which looks like this. Right, it's just y equals x squared, except not the left-hand side of it, because x equal to the square root of y, x has to be positive. And then x equal to 3 is a vertical line. So x equals root y to x equals 3, that's your left to your right boundary. So if it's x equals something to x equals something, it's left to right. Y equals to y equals, it's bottom to top. But here, our horizontal strip looks like that. We've got x equal to root y on the left, x equal to 3 on the right. And then the y limits, or the outer limits, are talking about how much this strip can slide up or down in this case. So the strip can go as low as 0 and as high as, I bet this point right here has a y value of 9. And it does. If x is 3, y is 9. Question?
Since we're like, if we can graph it, is there like a easier way how to
The answer to that question is kind of no, actually. So typically, if you are in a situation where you need to interchange the order of integration, graphing it is usually a necessity. Yeah, usually the graphing isn't too terrible. Like they're usually pretty standard, like graphs, like square roots or squares or cubes or stuff like that. But yeah, it's kind of a, I don't know of a better way to do it really. And I say better, but I really don't actually know of an alternate way to do it. Yeah, let's see.
Did you know that when x is 3 was just because it's the top of the two?
Right. So I figured that I was probably going to get, like, it wasn't going to weirdly cut off like here. I was under the usual correct assumption that I was going to get kind of the whole nice region there. But then when I actually plugged in 9 for y, which is the top line for y, I'm getting x equal to 3. But yeah, there's definitely, it's not a surprise that that point there is 3, 9, because we're thinking of that. So now the idea is we're going to take that same region, which you don't have to draw again, but I'm going to draw again. And draw it a little bit bigger. And instead of using a horizontal strip like this, we're going to use a vertical strip for the same region. So now the lower boundary of that strip is still y equal to 0. And the upper boundary of that strip, well, it was x equal to the square root of y, but now if we solve for y, it's going to be y equal to x squared. So, and notably, no matter where I draw the strip in this region, right? Whether I draw it way to the left or way to the right, the respective bottom boundary and top boundary are always the same, right? The lower boundary of that strip is always y equal to 0. The upper boundary function of that strip is always y equal to x squared, no matter where I draw the vertical strip in the region. Just like over here, when I draw the horizontal strip, the right-hand boundary was always x equal to 3, no matter how high or low the strip went. And the left-hand boundary was always x equal to the square root of y, no matter how high or low I went. And then after we figure out the bounds for our vertical strip, then we're going to ask ourselves the other question: how far to the left and how far to the right can you slide the strip? Or in other words, how far to the left does the region go and how far to the right does the region go? The region goes as far left as x equals 0. The region goes as far right as x equals 3. So rewriting this integral, it's going to look like the double integral from, now we're going to switch it. So we're going to go y is the inside. So y equals 0 to y equals x squared. Still the same function, 1 over the square root of x cubed plus 9. But now it's dy. So there's your inner integral. And the outside integral, after we do all the inside stuff, is going to be the integral from x equals 0 to x equals 3. You don't have to write the x equals, I just like to. Yes. Question?
And so, did you only use like the changing of like the order of the integration, and there's like kind of like x equals to like a square root of like y or something?
No, what I would say, we usually use this kind of idea of interchanging the order of integration kind of when we have to. The problem here is that this function actually is not anti-differentiable as a function of x, as it is. They're really, like literally, I don't know. There does not exist a function whose derivative is equal to 1 over the square root of x cubed plus 9. So that's usually the kind of impetus or reason for changing the order of integration. Because now, when we look at this integral, it's the integral of 1 over the square root of x cubed plus 9 dy. So we're integrating this with respect to y. We're pretending like y is the variable and anything that's not y is a constant. So you know what I see here? One big constant. Question?
I see this in the y equals on the equals change to like 0, 0, next to it.
Right. So what's happening here is this way of writing it. I'm writing this as, so here the inner limit of integration. So let's actually back up, because I feel like, so let's come back to this example because I want to do a few more examples. So I think it'd be good to practice. So we'll come back to you and let's do something like, sure. So let's say we want, so, well, yeah, we'll back up a little bit. So let's use some double integrals just to describe an area. For example, let's say we wanted to find, let's make it not too terrible. Hello. So let's say we have this region I'm about to draw here. This line here is y equal to x. This line here is x equal to 4. And I want to describe this region here using a double integral. There's a couple ways to do it. And so when I'm thinking about doing a double integral for something, or even a single integral, to be perfectly honest, if I'm trying to describe a region or an area, I want to think about what kind of strip I'm using. Am I using a horizontal strip or a vertical strip? And usually you can kind of choose either. The deciding piece of information is often which kind of strip is always going to have the same kind of boundaries. So here, if I use a vertical strip, no matter where I draw the vertical strip in this region, the top function is always the same and the bottom function is always the same. So here a vertical strip is a great choice. If I want to think about how to write the area here, well, let me actually show you all. One way to write the area using a vertical strip or a vertical rectangle. I could do it using one integral. I could say, oh, great, this area here is equal to the integral from, let's see, 0 to 4 of the top function minus the bottom function. Which I know is maybe a little more than you would need to usually write, but that's okay. We're doing it for. Here's what I want you to know. You could also write this as a, and actually that's actually calculated as well. That's going to be the integral of x, which will be x squared over 2 from 0 to 4, which will be 4 squared over 2 minus 0 squared over 2, which is 16 over 2, which is 8, my favorite number. Great. But we could also do it this way. We could say, I'm going to write this as a double integral, where now the inner integral is actually describing those upper and lower boundaries. So the lower boundary here really is the line y equals 0, and the upper boundary here really is the line y equals x, which I know I already wrote, but oh well. So you've got y equals 0 to y equals x, and the of 1. And the reason we're integrating 1 is because basically you're trying to find a thing who's got the same area as this, and so we just want to use a 1. So I want to point out that this inner integral, let me ask everybody, what's the antiderivative with respect to y of 1? Y. And then you're going to plug in x minus plug in 0. So when you do this inner integral, you're exactly going to get x minus 0. And then the outer limits of integration are going to be exactly x equals 0 to x equals 4. And these integrals are the same. They look a little different, but they represent the same information. So if you're doing this the long way, actually writing out, you do the inner integral, you still have x equals 0 to x equals 4 on the outside. The antiderivative, like you all just told me, is y, and y is going from 0 to x. And then you would plug in the limits of integration for y. You would get still the integral from x equals 0 to x equals 4. You plug in x minus you plug in 0. And then we did this one before already, right? The integral from 0 to 4 of x is just going to equal 8. So you can write an area using a single integral like we've been doing for quite a while since midway through 16b, or using a double integral. But now we can also interchange the order of integration. So maybe for some reason it's really not helpful to me to do it this way. So I can say, let's do it a different way. Now this one's not going to be a super excellent example because the change, the order of integration is going to look very similar. Oh well, we'll do another example in a minute. So here's my horizontal strip. And now I'm thinking about the boundaries of that horizontal strip. The right-hand boundary is x equal to 4, no matter where I draw it. I could draw it there, draw it there. Right-hand boundary is always x equal to 4. The left-hand boundary is always still this line here. Now, the important thing to remember is that when we're doing a horizontal strip, we want x to equal a function of y. We want x equals something and x equals something. Yeah, Josh. It's a really, really good question. The answer is kind of, there's actually a number of good answers to that question. One answer, which I'll show you after this example, is the region dictates it. And so give me a minute to answer that question. Right now, we're just trying to show that we can do it both ways. So here, even though I'm thinking this is the line y equals x, I'm going to write that's the line x equals y. So I want my inner limits of integration to be x equals something to x equals something. So my inner integral here is going to be a left-hand limit of x equals y to a right-hand limit of x equals 4. And that's going to be a dx. Right, it's dx if you've got x equals to x equals. Now I'll point out, if you actually, well, in fact, I'll write it again. Just give me a second. And then my outer limits of integration are just like how before, how we said this red vertical strip goes far left as x equals 0, as far right as x equals 4. Now this horizontal strip can go as far down as y equals 0 and as far up as y equals 4. This double integral represents the same region. It's a little bit different. Right here, you're going x equals 0 to x equals 4, y equals 0 to y equals x. Here you're going y equals 0 to y equals 4, x equals y to x equals 4. Kind of like with partial derivatives or mixed partial derivatives, you kind of want to read this from right to left, or as really I would say it's from the inside out. I'm thinking about what's happening on the inside here and then on the outside out. Most books would write this integral as integral from 0 to 4, integral from y to 4 of 1 dy dx. They don't write the, oh, sorry, I messed up the order there. I apologize. That should be a dx dy. Let me just scratch that out and write it again because that's terrible. It should really be this. Sometimes they don't write the 1. You'll see textbooks just write dx dy here. The 1 is implied. So when it's a dx there, I know that means my inner integral is x equals y to x equals 4. When it's the dy on the outside, it means my outer limits of integration are y equals 0 to y equals 4. For any definite double integral, the outer limits have to be constant. Cannot have the outer limits have variables in it. It's not, it doesn't work. Because when you're integrating this thing, when you do the last integral, you have to be able to plug in constants so you actually get a value that's representing either some area or some volume. Let me calculate it real quick. If we integrate this, the integral of 1 is x from x equals y to x equals 4. Then we integrate that, or sorry, we plug in, apologies, the integral from 0 to 4 of 4 minus y dy. Then we integrate that. Sorry, we're going to go up here. We're going to get 4y minus y squared over 2 from 0 to 4. And then plugging in, we get 4 times 4 minus 4 squared over 2 minus 0 minus 0. And 16 minus 8 is 8, just like before. So even though you get a little bit of a different path to get to the right answer, we still get the same right answer no matter if we do it with y first and then x, or x first and then y. But we do have to change the limits of integration so that they represent the region, right? These limits of integration, I didn't just swap x for y and things. I actually had to look at the region and see what I had. So let's address the question Josh asked. I think was a good one. How do we know when to use what? Well, it kind of depends. Here's an example. Let's say I want to describe the following region. Do I remember what it is? Yeah, sure. The region bounded by y equal to the square root of x, y equal to 6 minus x, and y equal to 0. This is the boundaries of our region. Here's y equal to the square root of x. Here's y equal to 6x. Sorry, 6 minus x, apologies. And here's good old y equal to 0. And be careful, it's easy to grab the wrong region here if you're not paying attention. It's going to be this part right here, not this part up here. If I had said x equal to 0, though, it would have been this part up here. So here's our region. We're trying to describe it in the way that's useful. Now, technically, either choice will be correct. You can use vertical or you can use horizontal. But there's a reason why you might pick one over the other. Let me show you. Let's use horizontal first. If I draw a horizontal strip, no matter where I place my horizontal strip in this region, the left boundary is always y equals root x. The right boundary is always y equals 6. But, in fact, here's how I really think of. Let me think about that before I say that. No, actually, I don't. I'm going to take that back. I'm not going to say that. Okay. So when you draw this horizontal strip, you're really thinking of going from left to right, meaning x equals something to x equals something. So usually that's going to mean we have to change our functions of it. So we're going to rewrite y equals the square root of x as x equal to y squared. And we're going to rewrite y equals 6 minus x as x equals 6 minus y. So then the inner integral is going to have a left-hand boundary of x equal to y squared and a right-hand boundary of x equal to 6 minus y. That's going to be a dx, because x equal to something goes with dx. And then, well, that, if I think about it, right, if I integrate this, what's the integral of 1 dx? Oh, dumb question. It's just x. And if it's x, that means you can plug in the things that x is equal to, right? It'd be wrong to have a dy here, because then you would get y, and you couldn't plug in x's for the y's. So it makes some sense. And then the outer limits of integration are going to be, well, how low do we go? 0. How high do we go? And whatever that point of intersection is there. So we're going to say, well, I need to know where square root of x is equal to 6 minus y. 6 minus x, apologies. You could actually square both sides and solve this, or you could just guess. I'm going to guess numbers that are easy to take the square root of, like 0. Nope, 0 is not the right answer. Or 1. Nope, 1 is not the right answer. Or 4. Yep, 4 is the right answer. Square root of 4 is 2. 6 minus 4 is 2. So these intersect at x equals 4. And then if x equals 4, y is going to be the square root of 4, or 6 minus 4, which is 2. So that point there is 4, 2. A lot of the times, these functions that intersect each other are going to intersect in a nice point, and instead of trying to actually solve the equation, you can guess a likely candidate for the solution. So that means we're going to go from as low as y equals 0 to as high as y equals 2. And then I guess we could calculate it. Why not? It's good to practice doing the integrals. So calculating this, integrating 1 with respect to x, we get the inner integral to be x evaluated from x equals y squared to x equals 6 minus y. And then we're still going to do the outer integral, which is the integral from y equals 0 to y equals 2 dy. Now we're going to deal with the insides. We're just going to plug in 6 minus y minus y squared. Notice this is what it would look like if you had just done it kind of the regular 16b way using horizontal cross sections. You do the integral from as low as y equals 0 to as high as y equals 2 of the right function minus the left function. And then you'd integrate 6y minus y squared over 2 minus y cubed over 3. Plug in from 0 to 2, you get 6 times 2 minus 2 squared over 2 minus 2 cubed over 3. I'm not going to write it down, but minus 0 minus 0 minus 0. Do check. Occasionally plugging in 0 doesn't get you all zeros. Like if there's a cosine of 0, that's equal to 1, or an e to the 0, that's also equal to 1. So just be like, a lot of the times plugging in 0 gets you 0, but not always. So just be careful. And then this would be something. It'd be 12 minus 2 minus 8 thirds, which is 10 minus 8 thirds, which is 30 thirds minus 8 thirds, so 22. So why would I do it this way instead of doing it using vertical cross sections? Well, if I use vertical cross sections, right, the vertical cross section here and the vertical cross section over here have a different upper function. It's still doable. It just is usually seen as less desirable because it's thought of as being more work. Set it up this way. So this was using horizontal cross sections up here. Sorry, bad labeling things. This is using vertical down here. To use vertical, well, I have to break it up right there at x equal to 4. So for the left of 4, my lower bound is y equals 0, my upper bound is y equals root x. So it's going to be y equals 0 to y equals root x dy, 1 there too. And then the x limits are going to be as far left as 0 to as far right as 4. So we've got x equals 0 to x equals 4. But that's not all of it, right? That's just the left side of this. And we also have to add on. Now, this other one here, I will point out this other one here if you're being slick.
You could just say it's a triangle whose base is 2 and whose height is 2, and use an area formula for a triangle, if you really wanted to. But in the spirit of what we're trying to get at here, the way you would actually calculate or write this integral would be, well, the integral would now be a lower bound of 0 to an upper bound of 6 minus x. And then a left bound of 4 to a right bound of 6. Still perfectly correct, but considered the less good way of doing it because you're having to write 2 intervals or something. So that's one answer to your question, Josh. Why you would do the using, in this case, horizontal versus vertical, because it's less integration to do. Now, one more second. A better answer to that question is because the way it's given to you is it's because it's impossible to integrate the function you're integrating in a certain way and not the other way. Hanson, yeah.
I'll just like try to make sure I understood it correctly. So as long as the top bounds and like are and the bottom of the lower bounds are like all the same, it's like either one.
Yeah. Yeah.
Okay.
So like if instead we were doing this section up here, this region up here, would we want to use a vertical strip or a horizontal strip to do that one? Don't say that out loud. So let me draw some vertical strips. Don't say anything. And now let me draw some horizontal strips. So of those two choices, which one have the same ends of the rectangle? Do the vertical rectangles will have the same ends, or do the horizontal rectangles will have the same ends? Okay, everybody, tell me what you think. Yeah, the vertical ones have the same ends. The vertical ones always have the same bottom function of y equals root x, and the same top function of y equals 6 minus 6. So this region here, I would definitely do using vertical cross sections. So just to point that out, we might as well do it since we're already here. We're not gonna do the whole integral. We'll just talk about it for a second. This is my region. Now the left-hand boundary is x equal to 0 here. I'm talking about this region here. Vertical cross sections are for sure the way to go. If I was trying to write this using a double integral, I'd say, okay, well, I'm always thinking of the cross section giving me the inner integral. I just can't help it. You should work from the inside out for these problems. That's the way to do it. So the inner integral is going to be, well, my lower boundary is y equals root x. My upper boundary is y equals 6 minus x. 1 dy. I know it's dy because it's y equals to y equals. And then I kind of like to put that in parentheses even. My outer integral is usually much easier. It's just asking how far can my strips slide. So if it's a vertical strip, how far to the left and how far to the right can it slide? You can slide as far left as x equals 0. You can slide as far right as whatever that value of x is there, which is 4. It's going to be a super small rectangle when it slides that far right, but it can still slide that far right. Or the other way you can phrase this question is, how far left and how far right does the region exist? And it exists as far left as x equals 0, as far right as x equals 4. And that's how you would do it. Now, again, just so you're clear on this, normally you would see this written in the textbook as the integral from 0 to 4, the integral from root x to 6 minus x. You might not even see a 1 dy dx. This means the same thing. It's just the more normal way of writing it. It is totally fine to write x equals 0 to x equals 4 and y equals root x to y equals 6 minus x. It's just not required, or typically done, I should say. Questions about this? Yeah.
Could you explain again, like, when to use the windows?
So for all of these problems so far, you could definitely have used a single integral. And in fact, interestingly, I think after you do the first step, you get the single integral that you would have just written. So for example, if I do the first step of this integration, if I integrate 1 with respect to y, I get still the outer stuff. And then the inner integral, well, the integral of 1 is y, evaluated from root x to 6 minus x.
Then we plug in, we get the interval from 0 to 4 of 6 minus x minus root x. Which is exactly how you would have set up the interval for this area in 16b. Right? Interval from as far left as 0 to as far right as 4, top minus bottom. The reason we're doing this is because we're not using a defined area. That's how we start off talking about it, because it's easy to kind of conceptualize. But the real idea here is, for example, I want to find the volume under the surface. It's not going to suck. F of x, y equal to, sure, 9 minus x squared minus y squared on the interval where, I'm just going to draw it. Sure, I'm going to draw something that's terrible. Fine. Yeah, I have to think about what we know how to do. Sorry, apologies. Sure, let's just make it not too terrible. Let's say it's over this interval. Y equals 2x. X equals 1. Y equals 2. So the idea is that we're taking this surface. In fact, ooh, maybe I can actually show you. Let's take a look. We'll see. That's short, I think. We'll find out. Okay. So the idea here, come on, yeah, I never won. I never won that. Oh, I did, of course, I clicked the wrong thing. Good job. Delete it all. Can I delete it all? Maybe. Sure. So we want to look at the volume under. Actually, let's do the region first. So we've got x equal to 1. Sure. Y equal to 2x. Sure. And y equal to 0. So it doesn't look super helpful. Give me a minute. So close. All right, it's hard to see what you're doing when you're way over here. You can kind of see it. Can you guys kind of see that? There, I lost it. Okay, there's your x-axis in red, your y-axis in green, and right there, in between those three planes, is the region that I am integrating over. And so what I'm saying is, in that region there, I want to then find the volume under that downward opening paraboloid. So it doesn't look like much from this angle, but right here, you can kind of think about, oh, I kind of see it's the volume under the shape, but just over that region. Which again, not super. Oh, I could probably try harder to like cut things off so I don't see them all, but hopefully that kind of gives you the idea. We're trying to find the volume under this thing, but just on that. So it's kind of like if you took this surface here and just cut that triangular region out until you got it. In fact, I could probably even try to draw it. So here's what we've got. Oh, ow, don't poke yourself with a pen, James. It's really smart. So here's the idea. Here's our paraboloid opening downwards, and we're over this region in the XY plane. So just to kind of show you, right, here's y equals 0. Over here is, say, x equals 1. And y equals 2x, sure, 1, 2, maybe it looks like right here. So it's kind of like this little triangle, and then going up like this, up like this, and up like that there. So there's kind of the parallel pipe bed kind of triangular prism shape that you've got. So for that, at least helps you a little bit think about what we're doing. And this is why we need a double integral, because we can't just describe this volume using a single integral. We need the double integral part to give us the region we're integrating over, and then the function we're integrating is going to be the thing that's the height of that surface. So here's how you set up the volume here. Well, I still made a double integral for the region. You could use horizontal or vertical strips here. If there's no reason to pick one or the other, my default is to usually use vertical because we're used to all thinking of functions as functions and as y as a function of x. So I would default to vertical, say great. My inner integral is going to be from y equals 0 to y equals 2x dy. My outer integral is going to be from x equals 0 to x equals dx. And the function I'm integrating is going to be 9 minus x squared minus y squared, which is going to kind of suck. Okay, you don't really need parentheses there. I shouldn't have written them. They're terrible.
Think on an exam, we would give us the equation like that, where it gives the balance and show the picture.
Good question. They would probably phrase it as in like, they probably wouldn't give the picture. They'd probably say, find the volume under the surface, z or f of x, y equals 9 minus x squared minus y squared over the region bounded by y equals 0, x equals 1, and y equals 2x. That's probably how they would say it. It was just easier for me to draw because I was making it up. So how do we do this? Well, just like with partial derivatives, double integrals, when you integrate, like when we differentiate with respect to one variable, you treat everything else like a constant. So here, I'm going to integrate with respect to y, anything that isn't y is a constant. Now be careful. We're not differentiating where you get the derivative of a constant to be 0, we're anti-differentiating. The antiderivative of a constant is the constant times your variable, right? The antiderivative of 6 is 6x. The antiderivative of 9 here with respect to y is going to be 9y. We're going to get, leave the outsides alone for a minute. The insides are going to be, well, the integral of 9 is 9y. The integral of the constant x squared is going to be x squared times y. And the integral of y squared, not a constant, that's a variable. The integral of y squared is going to be y cubed over 3 from 0 to 2x. Probably didn't need to write this quite so largely. And then you plug in 2x for every y, which is y, unintended. I like to write y equals here. So I know where I'm plugging those things in. I'm going to plug in y equals 2x for every y. I'm going to get the integral from 0 to 1 of, let's see, 9 times 2x minus x squared times 2x minus 2x quantity cubed over 3. And then let's see, if I plug in 0 for every y, if I get 0 minus 0 minus 0, I'm not going to write it down. But you do need to check. Okay. I would maybe not maybe. I would definitely simplify this first. So I'd rewrite this as the integral from 0 to 1 of 18x minus 2x cubed minus 8x cubed over 3. No, I don't want to combine those into one term with x cubed because I don't want to add fractions. I'm just going to integrate now and get 18x squared over 2, 9x squared, minus 2x to the 4th over 4, minus 8x to the 4th over 4 times 3, from 0 to 1. The great thing about the limits of integration from 0 to 1, if everything is just the power of your variable, is you just get the coefficients. So I'm just going to get 18 over 2 minus 2 over 4 minus 8 over 12 minus 0, 0, minus 0, minus 0. This is going to end up equaling 18 over 2 minus 2 over 4 minus 8 over 12, which is something, right? It's 9 minus a half minus 8/12 is what, 2/3. Great, that's a good enough answer. Sure, you can make it better if you wanted to. I don't want to. So this is the reason why we do double integrals. That's not the only reason.
But one of the things we use double integrals for is to find the volume under a surface. And you kind of have to do it this way. There isn't really any other option. And we got it. Cool. So let's see. What? Sure. How about this one? Do I want that one? Try that one. Let's say we want to find volume under the surface, d equal to 1 minus y over the region in quadrant 1, sorry, in the first octant, not first quadrant, bounded by x squared plus y squared equal to 1. Okay. Sure. So it says find the volume under z equals 1 minus y over the region in the first octant bounded by x squared plus y squared. X squared plus y squared equal to 1 should sound kind of alarm bells. What kind of shape is that? Oh, kind of, well, yes, it's a two-dimensional sphere. Circle. So what we've got here, if I'm going to try and draw this, because I want to draw it, if I know I'm only working in the first octant, I'm just going to draw it so it looks like everything's positive. So that's a circle of radius 1. There's a 1, 1. So there's the quarter of that circle in the first octant. And then z equals 1 minus y, that's a plane. It's got a z-intercept of 1. It's got a y-intercept of 1. And x can be anything. So what's happening is kind of, I've got this plane here, and then it's kind of just coming out this way. So it's going to kind of come out this way like this. Straight down here, but then it's going to kind of curve around here like that. So you've taken this plane that was going like down from left to right like this, and well, back to that paper, right? Taking this plane coming out at you in the x direction, and we're cutting it with this circle. So we're only getting part of it. And we're getting everything that's under it, but under a circular part, which I know it's not like, not the best, bless you. Yeah, it's kind of like you cut this with the corner of a circle, you would get some amount under it that was kind of, that's how. That's what it kind of looks like. Now, how about the setup? Well, all right. To calculate the volume, we're going to do the double integral over the region of z as a function of x and y dA. This is the very kind of general thing your professor might write, where they're just saying there's a region, it's either dx dy or dy dx. We don't know. We're going to figure it out. Okay, so let's see here. To draw the region, I should just draw the region in the xy plane, meaning, okay, here's my xy plane. Quarter of a circle, that's a 1, that's a 1. And the equation of the circle, well, I still know it's x squared plus y squared equal to 1. Okay, I don't have any intuition as to whether I should use vertical strips or horizontal strips, so I'm going to go with vertical, because there's no good reason to not. At least not that I know of yet. So my lower boundary is going to be y equals 0. My upper boundary is going to be y equal to the square root of 1 minus x squared. We're just solving this equation for y. It's not plus or minus, it's just the plus because I've only have the top half. Yeah. No, that's definitely y equals 0. So this lower boundary here, the x-axis is y equals 0. Sorry, you might have thought I meant this though. So then this is going to look like, so my y's are going from y equals 0 to y equal to the square root of 1 minus x squared. My function is 1 minus y, and then my outer limits are as far left as 0, as far right as 1. Oof. So now I'm worried this isn't going to turn out well, but sometimes it happens. So
Yeah. Okay, so integrating with respect to y. The integral of 1 minus y is y minus y squared over 2. From y equals 0, y equals the square root of 1 minus x squared. Plugging in, I'm a little worried about this. Oh, I'm not worried about this actually. It's okay. It's going to be the integral from 0 to 1 of the square root of 1 minus x squared minus the square root of 1 minus x squared squared over 2. Of course, I'm gonna run out of room though. So let's simplify this a little bit. And square root of 1 minus x squared is just going to be 1 minus x squared. Now the problem is this part here is totally easy to integrate. We can simplify it, no problem. But the integral of square root of 1 minus x squared is something we don't know how to do in this class. That's okay though. I'm going to break this up as the integral from 0 to 1 of the square root of 1 minus x squared minus the integral from 0 to 1. Let's pull out the 1/2 and just say it's 1 minus x squared. Okay. Yes, why am I not worried? Well, that part there, that's a geometric shape we know. Y equal to the square root of 1 minus x squared is the top half of a circle. And if you're only going from 0 to 1, that's a quarter of a circle of radius 1. And this is literally, if this comes up on a test or the homework, this is what you're expected to do. The expectation is just to be like, oh yeah, that's a circle. And I know that's a quarter of a circle. This is 1/4 of a circle with radius equal to 1. So the area of that is going to be 1/4 pi times 1 squared, which is pi over 4. And then this other part, we just integrate like usual. So we're going to end up getting pi over 4 minus 1/2 times the integral of minus x squared is x minus x cubed over 3 from 0 to 1. We're going to get pi over 4 minus 1/2 times 1 minus 1/3. Minus 0 minus 0. So then we get pi over 4 minus 1/2 times 1 minus 1/3 is 2/3. 1/2 minus 2/3 is 1/3. So you end up getting an answer of a volume of pi over 4 minus 1/3. Which I would just point out is positive. Because I was like, is my volume actually positive? Yes, it is. Great. I'm happy. Okay, so I would encourage, if you haven't already, I would definitely encourage you all to watch the video I posted. There's a lot more examples of double integrals, including examples where we talk about kind of stuff that's impossible to integrate one way and then do the other way. And then on Friday, we'll talk more about double integrals as well, unless we really need to move on to sequence. Have you guys started talking about sequences in class yet? Okay, all right. So we'll maybe talk a little bit more about double integrals on Friday, but we'll probably start talking about sequences. I highly encourage you. If you haven't watched the video I posted over the weekend, please watch it. There's a lot of good examples in there.